let's dive in. Probability distributions. What in the world is a probability distribution? I don't know if this lecture stuff is helpful at all for you as much as doing actual homework problems. I'll definitely get to the homework. I don't know if these definitions make a lot of sense. It's the concept of a random variable. That just means a variable that can randomly change numbers. And the concept of probability distribution. A probability histogram is a graph of that. That's probably enough said. Let's move on. So random variable, we usually use X, is a variable that has a single numerical value determined by chance for each outcome. So, let's see. So probability distribution, description that gives probability to each value. So again, a bunch of words. An example I think will be most helpful. Discrete means, remember we've talked about discrete and continuous before? Discrete just has like separate values, whereas continuous, we talked about the clock, like an analog clock, continuous clock versus a digital clock. It's that same thing again. Remember, and Brian and I had trouble saying it well, right? Remember the difference between, so discrete has certain set values, whereas continuous, the next screen, continuous. So an example would be if I said, all right, what's the weight of the men on the Fresno's? What's the average weight of the men on the Fresno State football team? So that's a continuous random variable, meaning that could be the average weight could be, I don't know, 196.2137465. Really. Now you think, well, nobody's going to measure it that way. Yeah, they're not. They're not. That's true. But if we just say average weight, we mean, the real average weight could go on and on and on as a decimal. It could be any value, in other words. Does that make sense? It doesn't have to be 196 or 197. Now, if we said average weight rounded, so this would be continuous. Am I making any sense? I'm feeling like this concept is still not making any sense. So, if I said average weight of the men on the Fresno State football team, that would be a continuous random variable. And if I said average weight of the men on the Fresno State football team rounded to the nearest pound, then that could be like 196 or 197 or 198. If you rounded it, then it would suddenly become discrete. Is that making sense? It would be discrete if you rounded it. It would be continuous if you just talked about the true value, because the true value could be anywhere. How are we doing? Is that making any sense at all? Maybe the examples will make more sense when they get to the problems. Okay, and now here's the requirements for a probability distribution, which probably still seems like this weird out there thing until we get to an example. Basically, it's got to be numerical, not categorical. We'll see an example. The sum, that Greek E, that means the sum. That means add up. It's been a while since we talked about that, huh? That means add up the probabilities, they equal 1. We'll see what we mean in a minute. And every probability must be between 0 and 1. So again, I know it's too fast for you to write all that down. Here's finally an example. This will make more sense, I think. Suppose we're talking about tossing a couple coins, We're going to flip a coin, or one coin twice. Number of heads. Oh, 2 coins. 2 coins are tossed. So if I'm going to, flip 2 coins, what could happen when you flip 2 coins? You could get, let's just go through the possibilities. You could get heads and then heads, right? Or heads and tails. Or tails and heads. Or tails and tails, right? 4 different things can happen, huh? When you flip 2 coins, okay? Now, they're saying number of heads. So you could get 0 heads. That's this case, huh? What's the chance you're going to get 0 heads, meaning 2 tails? What's the chance of that? 1/4, huh? Because there's 4 different things that can happen. Chance of getting 2 tails is 1/4. How are we doing? Am I making some good sense there? So the chance of getting 2 tails, no heads, same thing, different way of saying the same thing, is 1/4. what's the chance? So, in fact, I'll just write it right here. No heads means tails, tails. And what's the chance of getting one head? Yeah, it's both those put together, 2/4, a half, 0.5. Making sense? Because it could be tails, heads, heads, tails. Both ways there, tail, head, and head, tail. Either way, that's a half, because it's, right, 1/4 and 1/4, 2/4, it's a half, 0.5. That's why they have the 0.5 out here. See, the P is the probability of these various things happening. At the near the end of the hour, or no, the end of about an hour, probably an hour and 15 or 20 minutes in, we're going to look at, you know how the overtime rule for pro football games, you have if two teams tie, what they do with that? What do they do when two teams tie in a football game to determine the overtime? Well, regular season they just let them tie, huh? Or yeah, they flip a coin, and the team that wins the toss gets the ball first, and that kind of stuff. So the question is that fair? Is that, because you want it to be fair, right? You want to give the two teams an equal try. Does the coin toss, the winner of the coin toss, have an unfair advantage in winning the overtime football game? Mm-hmm. And we'll look at the statistics behind it. We'll simply look and say, does the team that wins the toss end up winning the game a lot more or a lot less? If so, that means that's not a fair system. We can actually use statistics to analyze how fair. There's actually been a lot of talk. You can go on Google. There's tons of talk. It's already known. The answer to that question. We'll see it statistically. Anyway, so we'll be tossing a coin at that point. So what about, finally, two heads? So that's just head, and what's the chance of that? 1/4, 0.25. So that is what we mean by a probability distribution. So we're doing something, we're flipping two coins, or one coin twice, same thing. And there's different things that can happen. You can get 0 heads, 1 head, or 2 heads. And there's various probabilities that go with each of those. That making sense? So that's what we meant in all those things. Now, what do all those probabilities add up to be?
1.
They have to add up to be 1, don't they? That's what they meant back here when they said all the probabilities have to sum up to be 1. They have to add up to be 1, right? If we add all these up, it's 1.00, huh? Just think about money, right? A quarter of 50 cents, and another quarter, it's $1. 1. Of course they have to add up to be 1, because that's everything that can happen. You're either going to get no heads, 1 head, or 2 heads. Right? You wouldn't flip the coin twice and say, hey, did you get no heads, 1 head, or 2 heads? None of those. No, it has to be one of those. Right? They have to add up to 100%, don't they? So that's what they mean when they say the probability has to add up to be 1. 1 decimal is the same as 100 percentage, as we've talked about, right? And not only that, they're numerical values, right? These are numbers, aren't they? These are numbers. And then they said every probability is between 0 and 1. That makes sense. Every one of these probabilities has to be a number between 0 and 1. So that's what they mean. Make more sense now that we see an example? That is a probability distribution. They call it distribution because you're distributing the different probabilities to the different things that can happen when you do that experiment. Okay. We'll also look at gambling tonight. We'll look at some of the probabilities of that. I think that's very interesting. All right. So back to the coin toss. They're basically going to talk through all this stuff. They're going to say what I just said. Every probability 0 and 1 adds up to be 1. Numerical. There's the coin toss stuff. Then they're going to draw basically a bar chart, histogram, same thing. For that, right? You could get 0 heads. The chance is 0.25. You could get 1 head. The chance is 50%. 2 heads, and that's just the same thing put onto a bar chart, right? Nothing deeply amazing there. I made an experiment. This is part of what I did over my weekends. I did some prep for, because I haven't taught this for 15 years, so I'm working on, you're my project class this semester. I'm working on it as we go. And I made up, we're going to, in a week or two, you guys have your phones with you when you come to class, right? I'm going to try this thing I've never tried before, but I think it'll work. Where we're going to do a dice rolling experiment, and we're all going to enter it into, I made a Google Sheets. You know Google Sheets? Like Google Docs. Same thing as Google, where it's live and everybody can enter their data into it all at once. So anyway, I spent some hours, so I'm excited about trying that. It might just bomb and go terrible, but I think it'll work. So we'll all enter data like all at once, and we'll see the graph create all at once from all of us typing in data on our phone. Anyway, we'll see. It's way more techy than I am ever. I'm really terrible with tech, but so it'll probably bomb. All right, so let's look at another. So here's another probability distribution. Job interview mistakes. Hiring managers are asked to identify the biggest mistakes the job applicants make during an interview, and the table below is based on their response. Data from DECO survey. Does the table describe a probability distribution? Is that a probability distribution? Remember the three conditions, the three rules? Let me refresh your memory. Back here, there were three rules. Number one, they have to be numbers. The probabilities have to add up to be 1 decimal 100 percentage, and each probability is between 0 and 1. Let's go back. All right, what do you think? Is that a probability distribution? What are some of the problems it has? Les?
4.57.
Yeah, the total's a problem, huh? Yeah, it can't total more than 1. Everybody have a cold? I finally got it. I'm struggling to get over it here. I think almost every single person I know has a cold or has had one in the last week. All right, so you can't be over 1, right? That's a problem. So first off, that wrecks it. What else? It's got one other problem. What are these supposed to be? They're supposed to be numbers. Yeah, good eye. I don't know if you noticed. It's supposed to be numbers. This is a distribution, but it's not a probability distribution. These things are supposed to be numbers, not words. Even though, that's still a valuable thing and maybe useful for all kinds of things, but it's not fitting the condition of a probability distribution. Those have to be numbers, and this has to add up to 1.0.
So you graph it, stuff like that, is that way?
Well, first off, for the, why do they want numbers?
Yeah.
I guess so. Yeah, because, it's a good question, Val. Because I still think it'd be pretty useful to have those words, and you can still put those on a bar chart. Honestly, I really don't know. How about I just say I don't... But yet your guess is as good as any I would come up with. Maybe so. For whatever reason, they just want numbers in there. Yeah. All right. So those are the reasons. So what's the number one reason people don't get a job? According to this thing, anyway. They dress wrong for the thing. I'm maybe I'm a little sarcastic, probably. But you know that. All right. On we go. You'd probably not get the job with that. All right. Job interview mistakes. So anyways, we went through that. They're just talking about the problems there. Parameters, probability distribution. They're giving me a bunch of formulas, which you will not have to do because you have the wonderful calculator. It's going to do it for us, right? So we can just laugh at all those crazy formulas, and I'll show you how to do it on the calculator. Same thing with that one. On we go. Expected value. We will calculate, actually the calculator will do that one for us too. Expected value is going to be super important. It's like a probabilistic average. Very interesting. We'll see it when it comes to gambling and some other things as well. Very interesting. The applications are fun, I think. All right, so back to the example with the coins. So here's the coin example. Again, same thing. You had no heads, 1 head, 2 head. So let's figure out now. They're going to ask us to figure out 2 things, I think, if I remember right. Yeah, they're going to want us to figure out the mean, the variance, and the standard deviation. They're doing that big, ugly table. We're not going to do any of it. We're just going to use the graphing calculator. So let's go back. Let me show you how you do this on the graphing calculator. Let me see if I remember. I'm about a chapter ahead. So I learned this about 2 weeks ago and did it like 3 times. So maybe I remember. So here, let me get a fresh screen. That might be a ways ahead. Yeah, I get it. All right, let me get a fresh screen. Uh-oh, it's a long ways. Yeah, so I'm going to go number of heads. I'll make the table again for you, and then we'll 0, 1, 2, and probability, right? And the probabilities were, what were they? 0.25, 0.50, and 0.25, right? That was the table. So let's put that into our graphing calculator, and I'll show you how to come up with stuff. So, put it in, hit stat button, and just put it down L1 and L2. Just first off, just put it down your list 1 and your list 2. So that's the first thing. So just take your graph calculator, just put that down, list 1, list 2. Remember how to clear them if you need to or whatever. Where is that? Oh, stat? Yeah. Go to edit, right, and go up there and hit clear, clear them out. Remember how that works? And then just put 0, 1, 2 down at list 1 and list 2, 0.25, 0.5, and 0.25. All right. So you got that in to the stat, and then, edit, and it goes right in there. Put that in there. And then when you're done, then you hit, so that's step 1, put the information in. Step 2, hit the stat button again, stat button, and then we're going to calculate, right? So you move on over to calculate, just like we normally do, and then hit enter, and enter. And what you'll see on the screen is it'll say, doesn't it say one var stats like that? Now there's some newer versions and some older versions of the TI. I have the older one. Yours might, does yours offer something else?
1 var, 2 var, medium, med.
Oh yeah, just hit enter on the one, just hit enter right there. You're on 1 var, right? And then you get, do you get the 1 var stats on the screen? Yeah. Everybody get the 1 var stats? And then at this point, what you need to do is go L1, comma L2. Now, how do you get the L1? It's down there. Remember, it's down. To get that, you hit second and 1. And to get this, you hit second and 2. And put a comma. Notice I put a comma in between. The comma is located kind of in the middle left above the 7.
Where it says list, frequency list, and calculate?
So just hit second and 1 and second and 2 here. I'll bounce around like yours, Eddie. So, yeah, can I see? You guys, is yours like Eddie's? Yeah, you guys almost all have this kind. Let me show. So your guys, you're seeing list and then frequency list. Is that what you're all seeing? And mine just has this because it's old. And then calculate. Yeah, so I think you just go L1, comma L2 right there.
It won't let you add the...
Won't it? Oh, I thought... See, I just got mine to work. And what you guys need to do is, you just put the L2 on the second line, and then just hit enter after that.
On the frequency?
Yeah, right. On the frequency, exactly. Just put L1 on the list, L2 on the frequency, and then just hit enter on the calculate. And you should get the stuff. And here's what you should get. You should be seeing X bar equals 1, and...
So you put second and L2, correct?
Yeah, right. Those are second. Well, second, right. For both of those.
Alpha would be for the green buttons, right?
Yes, exactly. That'd be if you needed the green. Right. So we're just doing second and 1.
Mismatch. Quick go to. That's what it said, huh?
And this one will be second and 2. And you should get some x is 1, some x squared is 1.5, and down below you get something called sigma of x is 0.707. So where are the answers that they're asking of us? It would be right here, this x bar. Remember that always means average. So that's what do they want? A mean. That's mean, huh? They ask for mean. So that's your mean right here. They're going to ask for mean, and your standard deviation is right here. The 0.707 number. Is that making sense? So the x bar is the mean. That always means average, right? And sigma, that weird little Greek symbol, that means standard deviation.
And the EX equals, or the X is what again?
We don't need these things. But what it means is that means add them up. It's a Greek S is what it is. It means sum them up, but we don't even need them. All we need is these two things, the mean and the standard deviation. So that means the average, what that means is the average value when you flip a coin twice is 1 head. And that makes sense, doesn't it? Does that make sense? If you're going to flip a coin twice, how many heads do you think you're going to get on average? One head. That's what this is telling you. You're going to get one head on average. But you're not always going to get exactly one head. There'll be some variation. Sometimes you get two, sometimes you get none. This is the average amount of variation, the standard deviation. That's what standard deviation is. We'll keep talking about standard deviation all semester. Hopefully it'll make more and more sense to you. It's the average amount of difference from the middle on that. All right. So we won't need to do all their fancy table stuff. Let's get back to the question. Where was that? There. So we don't need to do all that. See how they got the same standard deviation we got down there? 0.707. They got the same thing we got. And where's their X bar? I don't know. I don't see it. Oh, there it is. There it is. That's their mean. I'm not even going to mess with variance. Who cares?
Square says 0.707.
Yeah, it's just the square, but I'm not even going to bother to. I don't think it's in the homework. So if it is, I'll do it then. So there's the standard deviation that we got, and there's the mean that we got. We got them right from the calculator. We don't need to make those tables or do any of that. Is that good? We all good there? All right, let's keep going. So what does that all mean? When tossing two coins, the mean, the average number of heads is one head, and the standard deviation is 0.7. All right, let's keep going. Now we're going to talk about significantly high or low results.
Thank you.
Remember what significance always means? It'll be the same thing all semester. 5% or less, huh? Something's considered significant and not just luck if the chance of it is less than 5%. Less than 5%. All right. And same thing for significantly low. And then expected value, that's just average. That's like what we just did with the coins. What's the expected number of heads? It's 1. All right. Let's look at a betting problem. You have $5 to place a bet in the Golden Nugget Casino in Las Vegas. You have narrowed your choice to one of two bets. Bet on the number 7 in roulette, or in craps, bet on the pass line in the dice game of craps. Which one's a wiser bet? Gambling is a science. That's you. All right, so let's take a look. So that's what we're going to analyze now with statistics. All right, here we go. If you bet $5 on the number 7 in roulette, the probability of losing the $5 is 37/38. Is that making sense? How many numbers around that roulette wheel?
30.
36, and then 0 and double 0. So 38 total. So there's the numbers 1 through 36, and then there's the green 0 and the green double 0. You guys remember that? No? Yeah. No, I don't either, but I don't for a scientific reason. Let me show you exactly why. Well, and a moral reason as well. But let me show you why. But when you're done with this, we'll understand that the casino always wins in the long run. That's the main thing to be wise on. So let's take a look at this. So 37. So there's 36 numbers, 1 through 36. There's a single green and a single double green. So there's 18 red numbers, 18 black numbers. That's 36 numbers. They alternate red, black, red, black, red, black. Then there's a single green and a double green. The casino always wins. We'll see. All right, so if you bet $5 on the number 7, if you put down $5, there's a 37 out of 38 chance you're going to lose that $5, right? Because there's 38 numbers. The chance it's going to be your one number is only 1 in 38. But if you win $175. So if you put $5 down on one number, there's just a 1 in 38 chance your spot's going to come up, but you win $175. But there's a very good chance you're going to lose $5. So the prize is actually $180, but they take your $5 bet, so your net gain is $175. Does that make sense? We're being all scientific about this. Find your expected value. Find your expected value if you bet $5 on the number 7 in roulette. This is the calculations the casinos live and die by, and live they do, by this calculation. This is it. This is their baby. Expected value. Expected value. What expected value is average result in the long run. Let's see it happen. So that's what we just did in our calculator. With the X bar, that's expected value. Let's see it. So, and then the other one is the dice game. Let's skip over that. We'll come back to that. So let's go to the roulette examples. Here's the roulette table. There's basically two different things that can happen at the roulette table. You can lose $5, right, to your bank account, down $5, or you can gain $175. The chance, and then here's the probability. Remember, a probability distribution is the different things that can happen and the chances of them. So you can lose $5, and the chance of that is very likely, 37 out of 38, that's the probability. Or you can gain $175, and the chance of that is 1 out of 38. Does that make sense? That's the exact numbers. So what does that mean? Well, if you multiply x times b, well, we don't even need to do all this. We can just do it on a calculator. You guys have a calculator? Let's just put it into our calculator. So what I mean is, this is going to be L1 here. This is going to be L2 here. Put in -5 and 175. Put in 37. Just divide. Just go 37 divided by 38 for that box on your calculator for L2. And do 1 divided by 38 for that box. Am I making any sense? So it's going to be L1 is going to be -5 and plus 175. L2.
You can actually, I don't know on the calculator, you can actually well, I was just going to say that you can actually, while you're putting in the numbers, you just put 37 divided by 38 and it'll just plug in the decimal.
Yeah, it just does it automatically. It's kind of nice, huh? Yeah, just simply divide and it does it for you. Yeah, it's real nice. Final answer, -0.26, whatever. Is that making sense? You guys able to get that in the calculator? Yeah, what does that number mean now? So,
unlikely you'll win.
Yeah, that means that's -26 cents, huh? What that means is, on average, every time you play this game where you bet on one number and you do the thing, you're going to lose 26 cents.
On top of your $5.
No, total. No, that's total. So notice, because you might think, wait, but yeah, you're betting 5, and so now the reality is you can't lose 26 cents. Right, sometimes you'll lose your $5, most of the time you'll lose your $5, every now and then you'll win the $175 back over. You play like thousands and thousands and thousands of times. Then all night, just betting on the roulette table, it'll come out to this average almost exactly. It'll be like you gave them 26 cents every roll. Does that make sense? That's what expected value is. It's the average amount of gain or loss, and it's always loss. They have calculated the expected value for every casino game, and it's always negative. It's always in the favor of the house.
So that if we knew how many times they rolled or how many they played, we could just calculate 26.
Exactly. Exactly. Yeah. Yeah. It's helpful. So that's what you can expect. You'll lose 26 cents per time you play on average. How about the other one? How about the dice game, craps? So we're going to do, where is it? We're going to, if you bet $5 on the pass line, I don't even know how it works. I don't know all the rules. But whatever, I'll just take what they're saying. If you can lose $5, that's the probability. If you win, you can make $5, and that's the probability. So long story short, here's our table. So let's do this one now. Here's L1. Here's L2. You can lose $5, and there's the probability. You can gain $5, and there's the probability. So try that one. Put that in L1, L2 real quick. Let's do the same thing. You guys getting that okay? I'm getting a little faster now. I got exactly their number. -0.07. You guys getting that? So that game is a better game, meaning you won't lose your money as fast. You'll only lose, on average, 7 cents per roll. You can play for hours without losing too much money on average. Does that make sense?
But you don't win it.
So if you double it and put 10 down, you're losing 14 cents. So
Right, of course. Yeah, this is for $5. You're right. You're thinking right, Eddie. Exactly. So if you double it, yeah, this is for a $5 bet. Well said. Exactly. If you double it or put $50 down, then it's times 10. You can expect to. Right. But this game actually, craps is a little more fair than the roulette table. I don't know if you know that. You can go on Google and find all that out. Craps is more fair. Blackjack and craps are the most equal games at the casino. Slots are the worst, and roulette tables below below craps and blackjack. So this means, on average, the casino knows you'll lose about 7 cents per game for betting $5. But then they have minimum bets, $10, $15, $20, because they want the money to go faster, right? So it's a science. It's a science for them. They know exactly what's happening. Does that make sense on that? So the question is, which one's a better bet? Well, basically, the craps game is a little better because you will not lose your money as fast. It's a little less negative on that. Does that make sense on that? I always like that because I always just want to cast. I think it's important. If you like gambling, feel free. Don't feel any condemnation. I'm not against it in any way. I've gone into casinos before, and with my wife, and when we took a trip years ago, and But so I think it's kind of funny and interesting. Sort of funny, sort of interesting. I remember my son, he was on a Frisbee tournament in Las Vegas a year ago, and him and his buddy went into one of the casinos. He said, yeah, we went in, Dad. We went in, and one of them went to a roulette table. One of us put $10, I think it was, or $20 on red, and the other put on black. We thought, one of us will win, right? One put $10, $20, I think it was $20 on red, one put $20 on black, and they spun the thing. It came up the green thing. They both lost. It's like, we couldn't believe it. We're just like, we're out of here. It's crazy. Anyway, but know this, that it is a science for them, and it's exactly calculated. They know exactly how fast they're going to make money. So what that would mean is if you're going to go into a casino because you think that's enjoyable entertainment, fine. Go in with the idea that I'm going to lose a certain amount of money at a certain amount of rate, and I'll have some fun, and it'll be entertaining. Great. You're doing great. They don't have you. But if you go in and you think you're going to win, that's when they've got you. So my goal in teaching this math is to enlighten people about the math. So if you're going to go in, you'll go in knowing you will be giving them some money. If you know that, you're safe. You're good. Go and have some fun. Kind of entertaining maybe kind of exciting. But no, you're going to give them some money. You're going to pay some money for that entertainment. Great. But if you go in thinking you're going to maybe win money, and you believe the stories of your uncles and aunts that tell you I've got an uncle and aunt that always tell me that, I always win. I think, I'm a math instructor. You're kidding me. I know better. I know you don't always win. I mean, you have your moments of winning and stuff, but long run, you do not win. You do not. I know mathematically. I don't need to be with you. Anyway, so this is the truth of the matter. So can I give you my one pet peeve? What would you think? So here's my one pet peeve with the casino industry. I do have one chip on my shoulder, and that is this. I think there should be truth in advertising. What would you think if smoking, you can't advertise smoking on TV anymore, right? Can't do it. It's illegal. They have to advertise billboards because why? The Surgeon General has determined that smoking is dangerous for your health, so they're not going to allow it to be done on TV. Right. Sounds good. So you'll see smoking ads and billboards and other places. What if you saw a smoking ad? Well, what do they usually say? When you see the advertisements for smoking, they make it look exciting, don't they? Smoke, you'll be an exciting person. It'll be an exciting life. I'm fine with that. Whatever. If people want to believe that, I think they're pretty naive. But whatever. But I would be a little upset if the smoking billboard said, smoke, it'll make you more healthy. Wouldn't you? If they said, smoke, it'll make you more healthy, I would be like, no, you can't say that. That's just a bald-faced lie. We all know. Surgeon General statistics are out. We all know smoking does not make you more healthy. That's just an in-your-face lie. And they don't. They don't advertise that way because that would be just ridiculous and rude and just crazy. Well, think about what the casino industry does. What are their ads saying? If they just put up ads and said, hey, come gamble, it'll be exciting, it'll be fun, you'll lose a little bit of money, but you'll have some fun. I would be okay. I'd be like, yeah, sure, do your thing. But is that how they advertise? What do they say? Winning! Winning!
One winner every week.
Winning! And you're going to win. They show these people winning.
Julie won $10 million.
Right. I'm sure she did. And for everybody else, they all lost. That is a bald-faced lie, isn't it? They know very well that you're not going to win. Not on the average. They know it. It's just like smoking, saying you're going to be more healthy. That's a bald-faced lie. If they would just say, come have fun, you're going to lose a little money, They wouldn't have any issue. I would have no issue with them. But if they're going to say winning, anyway, so there's my little pet peeve. Every time I see it, I go, I always point out to the kids, that's a bald, they've heard it a million times. Dad, we know all the statistics, whatever, anyway. So there's my beef. I think they should be held accountable for bald-faced lying. All right. Anyway, on we go. You know, they say gambling is what, the fastest growing addiction or something? People...
More suicide.
More suicide?
And gambling than any other addiction.
Wow. Yeah, bad. People lose their homes and all that crazy stuff. Wait, yeah, one more. Anyway, so, all right. Let's get to the actual problem. What was that last thing? Oh, yeah. So we already decided that. Let's get to the actual homework. So here we go. The table to the right, probabilities corresponding to numbers of girls in 3 births. What is the random variable? What are its possible values? And are its values numerical? All right, so is this a good random variable? There's question number 1 in the homework. We're on to the homework now. So number of girls, those are numbers, huh? That's good. Remember, they have to be numbers. Those are probabilities. It all looks good to me. I think it's all good. What's their question?
Well, I actually have the same question.
You have the exact same question, huh? I think the answer is the values are random and they're numerical. I think it's just that one, right?
Yep.
Yeah. All right, good. Let's move on. Okay, it's an easy one. On we go. Number 2. Is this, what's it saying? Is the random variable given in the table discrete or continuous? Yeah, remember we talked about that? So basically you want to ask yourself, are the values, could they be like any number or are they only fixed numbers? Only fixed numbers, right? You can't have 2.5 girls. You either have 0 girls, 1 girl, 2 girls, 3 girls in the births, right? They can't be any number. It's just got to be those integers. So that is discrete. That's discrete. Can't be continuous. It can't be any number. You can't say I had 1.2396 girls. It's impossible, right? You guys with me on that difference? Continuous can be any number. Discrete is just certain fixed numbers. This is certainly discrete. All right. And what's their second question? What does it want?
Why is it discrete? Because
the x values are, I don't know. What's all those boxes there? The random variable given in the coming table is, it's discrete because
the x values are numbers?
Has nothing to do with the... This one. There are, yeah, I guess it's that one. Are those all options? Yeah, finite number of values. Yeah,
No,
finite number of values.
There are, do we say there are infinite number of values?
No, there's finite, right? There's just five different possibilities. Finite number of values there. On we go. Number 3. For 100 births, probability of exactly 57 girls is 0.0301. Probability of 57 or more girls is pretty low. Is 57 girls in 100 births a significantly high number of girls? Which probability is relevant to answering that question? Okay, so what do they mean when they say is something significantly high or significantly low? What do they mean by that? It's all about the 0.05 number, huh? Yeah. So something is significantly high. Now, which probability do we care about there? 57 or more. That one. That's the one we actually care. You might think, well, what about this one over here? Well, that's just the chance that you have exactly 57 girls. Whenever you're talking about being significantly high, that means greater than or equal to that spot. That number or higher. How about I put it that way? That number or higher. So that's why the one we care about is this one right here, 57 or more girls. That's the probability that matters. So if we're trying to decide if having 50s, do you guys get the big idea of this question even? So now, yeah, let me frame. What do they even do in this question? What if they had some kind of new method, some medical thing to help you be more likely to have girls than boys be born? Okay? And what if they tested it out on 100 people and they had 57 girls out of 100? That's a little higher than we would expect, right? Normally we'd expect 50, right? So, but is that significant there? In other words, do we believe that method is actually causing them to have more girls, or could that have just been luck? That's what we're trying to decide. See what we're always trying to decide with the significant question? If there's less than a 5% chance, then we believe it's not luck. We believe that method's really doing something. So what would determine that? Well, it's the chance of 57 or more girls, not the chance of just exactly 57. Because exactly 57 doesn't matter. Maybe they could have had 58 or 59. That'd be even better. That'd make them, right? You don't want exactly 57. That's not what's going to prove the thing's working. I know this method's working because I had exactly 50. There was exactly 57 girls. No. 57 or more, right? There was a bunch of girls. That's what would prove the method is working. 57 or more, and they're saying the chance of that is 0.097. 0.097. So is that significant? No, not significant, because it's not under 5%. In other words, it's a 9.7% chance of luck. It could have just been luck that there was that many girls born. In fact, it's 8.097 or 9.7% chance of luck. That's too much a chance of luck. It could have just been luck. We don't believe with any confidence that the method really worked. How are we doing? Am I making any sense? I'm trying to read y'all, but you guys give me your poker face. I can't tell. Is that making sense or not? Is that good? So any time the chance of luck is under 5%, we call that significant. We believe that must not have been luck. So this came out more than 5%, so we don't believe that it's significant. We don't believe that the results are really dramatic, really believable. Does that make sense?
So we would say that was significantly high or significantly low?
Yeah, I see. That's what's confusing, huh?
Yeah.
Good question. Yeah. There's two things going on here. There's the number of girls being high, and then there's the percentage not being low enough. So in other words, let me put it to you this way. What if they tried this new birth control method, and they had 100 couples have babies using this method? Not birth control, I mean this kind of method to have girls. And out of the 100 couples, there was 98 girls were born. What's the chance that could happen by luck? Almost nothing. That has to be working, right? So if they had a really high number of girls born, like 98 out of 100, you would for sure believe the method's working. The chance of luck would be what? Super low, wouldn't it? Right? It'd be like 1% or 0.5% or something really low. So there's two things going on. More girls mean low chance that it was luck. Get the idea? 57 girls is a 9% chance of luck. That chance is not a low enough chance of luck. The number of girls is not high enough. The chance of luck is not low enough. It's got to be under 5%. There's two things going on there. Do you see that? So we're saying the 9% is not a low enough luck chance, because 57 girls, that could happen by luck. Is that good on that? Making better sense? So we would say it's not a significantly high number of girls, 57, because the probability is less than 5. Oh, not less than. Greater than. Sorry. Greater than 5%. Make sense? The percentage is too high. The chance of luck is too high, which means this is not a significantly high number of girls. So maybe if they had 65 girls out of 100, that would be significantly high because the chance of luck would be less than 5%. Good. All right. Let's try number 4. Determine whether the value is a discrete random variable, continuous random variable, or not. So for each one of these, we're going to do discrete or continuous. Remember, discrete means there's just a finite number of answers, not continuous. So number of points scored in a basketball game. Discrete. That's discrete, because that can't be any number. You can't do 2.3, right? The amount of rain in the city during April. That's continuous, yeah. Because that could be any number, couldn't it? There could be 2.314679 inches. There could be any amount, C. The response to the survey Did you smoke in the last week? That's not even a random variable. That's because remember it's got to be a number. Random variables have to be a number, not a yes/no question. That's what they're testing there. So it's discrete, continuous, or not even a random variable. So that's not even a random variable. They have to be numbers. It has to be a number answer. They could have asked, how many times did you smoke in the last week? That would have been a random variable. It's got to be a number. Number of free throw attempts before the first shot is made. That's discrete. That can only be a fixed different numbers, right? Can't do 2.5. The time it takes to fly from city A to city B. Yeah, that's continuous. That can be any amount of time, huh? That could be 3 hours, 10 minutes, 4 seconds, 0.3 of a second. You know, it could be. Yeah.
It's supposed to be B.
What's that?
B, the amount of rain.
In the city during April?
Yes, it should be
continuous. Yeah, it is continuous.
You
Put C for continuous.
C right here? C is continuous. Oh, I'm not doing A, B. I'm just putting C for continuous and D for discrete. Yeah, so it is continuous on that one. And then F, the number of people with blood type A in a random sample of 49 people. It's got to be discrete, right? It's got to be a fixed number. Those good? Those okay? Get more comfortable with the discrete continuous thing? All right. This will be on YouTube. If I'm going too fast, I just want to get through these for you. All right, number 5. When conducting research on color blindness in males, researcher forms random groups with 5 males in each group. The random variable X is the number of males in the group who have a form of color blindness. Determine whether the probability distribution is given. If it is, find its mean, standard deviation. Probably just not given, So they're giving me a probability distribution here. This is, they're taking a group of 5 males, and they could have none of them having color blindness, 1 of them, and 2 of them, 3 of them, 4 of them, or all 5 of them could have color blindness. What's the chance that nobody in that group, they just grab a group of 5 men at random, what's the chance that none of them are going to have color blindness, according to that table? Do you see it right there? Is that table making sense? If the chance, it's 66.4% chance, huh? So if you grab a group of 5 men, the chance that none of them will have color blindness is 66.4% chance. The chance that 1 of them will have color blindness is 28%, and on down you go. There's basically no chance that 5 out of 5 will have color blindness. So anyway, all they want us to do is put that in our calculator and hit the buttons. That's all we have to do. So just put that in for L1. Put that in for L2. So this side will be L1. This side will be L2. Let's see what we get. Excuse me. I'm getting 0.393 for the average. And the standard deviation, which is that sigma thing, 0.6037. I don't know how far to round that. So down here, the mu, that's the 0.393. It says round to 1 decimal place. I guess that'll be 0.4. And then the sigma, round to 1 decimal place, that'll be 0.6. You guys getting those numbers okay? Is that working out? I think I read this one before because I didn't even read it when I picked it. This is kind of goofy. Ted is not particularly creative. He uses the pickup line. If I could rearrange the alphabet, I'd put you and I together. That's pretty dorky, isn't it? I didn't notice it when I picked the problem a while ago. I might have X'd it out. But anyway, whatever. Okay, so the random variable X is the number of women Ted approaches before encountering one who reacts positively. Determine whether a probability distribution is given. If a probability distribution is given, find its mean and standard deviation. All right. So is that a probability distribution?
No.
Yeah, how do we know it's not?
They don't add up to it.
Yeah, that's it. If you add these up, I don't know what it is, but it's not 1.0, is it? You with me on that? It's not going to be 1.0. So this is a good question. We just say, no, right here, right? No, the sum of the probabilities is not equal to 1. So you don't even have to do the rest of the problem. You just keep going. The table is not a probability distribution. The table is not a probability distribution. And you're done. You don't have to put it into your calculator. Are we good there? Ted's crazy pickup line. All right. On we go. Groups of adults are randomly selected and arranged in groups of 3. The random variable X is the number in the group who say that they would feel comfortable in a self-driving vehicle. Would you feel comfortable in a self-driving vehicle? Determine whether a probability distribution is given. So out of 3 people, how many in a group of 3, how many would say they feel comfortable in a self-driving vehicle? Well, the chance that nobody would say they feel comfortable is 36%. 1 person is 43%. 2 people is 17%. All 3 people comfortable is only 2.5%, pretty low. All right, so is that a probability distribution? Is it not? I think they look like they're going to add up to 1.0 to me. If it looks close, don't even bother with it. It's probably good. I think only number 6 is the bad one. So that one's good. Can we just skip this one then? Then you just put in L1, L2, hit the buttons, blah, 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 same thing. That good? We'll just move on. Number 8. Okay, now we're going to look at a table. Describes the results from groups of 8 births from 8 different sets of parents. Random variable X represents the number of girls among 8 children. So, complete parts A. So let me look at here. On the next screen, there's the table. So we're having 8 births. You can have 0 girls, 1 girl, 2 girl, 3 girl, 4 girl, 5, 6, 7, and 8. And there's the various probabilities of having that number of girls. Let's go back. So find the probability. So now we're going to read the table. Find the probability of getting exactly 6 girls. So what's the chance if you have 8 births that you'll get exactly 6? Exactly 6 be girls. Let's go back to the table. So do you realize we just grabbed that number right there? 0.102. That's the one that's next to the 6. That's the chance of getting exactly 6 girls in 8 births. So we don't have to do anything with our calculator. Just give them that answer, 0.102. Next one. Find the probability of getting 6 or more. 6 or more. Let's go back to the table. How are we going to find out the probability of getting 6 or more girls? Just add them up. Exactly. So 0.018, 0.005. So you just add those up. Just use your calculator. Is that 152.125? So just add up 6 or more. Just add up 6, 7, and 8. 6, 7, and 8. So 0.125. That's the chance of having 6 or more girls. About 12% chance. Okay, which probability is relevant for determining whether 6 is significantly high number? So now we're doing the same thing again. We're saying, hey, if you tried some method of making you have girls, and you got 6 out of 8 were girls, is that significantly high? Which one of these statistics, which one of these probabilities would we use to determine that the answer to that question? It's this one, because that's 6 or more. I don't know if I'm making any sense of that for you. So the deal is, since the probability of getting 6, what is it? The result from part A or B. So it's going to be from part B. result from part B is the relevant, probably fewer is the complement result from part B. Yeah, boy, they're being tricky in their wording. It's actually D.
I got C. That's the exact same question that, like, well, mine is B, but B was the C. Like, this guy was saying.
You're telling me that the answer wasn't the complement one?
No, it was actually the C.
Let me check. Let me read that again and make sure I'm not crazy. But I think they messed up. Okay, so I'm saying I think they're wrong. I think they actually put the wrong answer. But tell me if I'm crazy. Let me talk it out. Maybe I'll see that I'm thinking wrong. If you have 6 or more girls, what does that mean you had?
7 and 8.
6 or 7 or 8, right? 6 or more includes 6, huh? You with me? If I said I've got 6 or more coins in my pocket, that's 6 or 7 or 8, right? If you had 6 or more girls, that's 6 or 7 or 8. When they say here, since the probability of 7 or 8 includes 6, no, it doesn't. That's just not true, right? If I said, hey, I had 7 or 8 girls, and somebody said, oh, you mean you had 6? You go, no, I had 7 or 8. Right? I think they messed up. So I guess they put the wrong answer down, but I don't want you to be fooled on the test. That's a mistake, it looks like. Right? Unless I'm thinking something crazy. I don't think so. Brian, you notice it? I think they're mistaken here, right?
There's
errors every
many
time.
times.
Yeah. Yeah, so this is a mistake, but I guess you're right, Andy, as far as they're choosing the other answer.
First, I don't want to take all this guy.
You noticed it call that. Good job. Yeah, anyway, but this, on the test, this would not be the right answer. Does that make sense? I'll make sure the test answers are right. That's not really
But
right
I get
answer.
it where they got it though from, like, because they're like referring to the question itself. You know what I mean? Like the question as a whole. So they probably said since the probability of getting 7 or 8 girls includes getting 6 girls, since we're talking about 6, 7, or 8.
No,
Never mind.
no. The way he reads it, that's wrong. It's
Yeah.
completely wrong. The answer they said is right.
Yeah, they're just trying to fool us, and then they accidentally put the wrong answer down. That's what happened, yeah. So this is not a true statement. Getting 7 or 8 does not include getting 6. Getting 6 or more would include 6, but getting 7 or 8 does not include 6, right? D is actually true. That's what doubly convinces me that they messed up, because D is actually true. Now, you might not be aware of it. Do you remember what complement means? It's been a while since we've done that. Opposite. Remember, it means opposite. So, since they're probably getting fewer than 6, what's the opposite of fewer than 6? 6 or more. Right? Since fewer than 6 is the complement opposite of part B, right? 6 or more is the opposite of fewer than 6. Yeah. So anyway, they just messed up. It should be that answer on a test. Just want to make sure we're all good. So they're being tricky in their wording there. They're being pretty tricky in their wording. But anyway, I want to get back to the basic idea. Do you understand the basic idea there? That whenever we're trying to decide if something is significant, we want to know if it's less than a 5% chance of luck, and we always mean from there to the extreme. So if we're saying we have this method for having more girls, we want 6 or more. We don't just want 6 girls. Right? Nobody would say, we're taking a special treatment to have more girls, and we really want exactly 6. No, they want 6 or more, don't they? They want more and more and more girls. Not just exactly 6, but 6 or more. Does that make sense? The significant thing always goes to the end. Do you know what I mean by the end? To the all 8 are girls. Not just 6. That's what they're trying to fool you with. Do you see that difference? Right? Whenever you're doing something, like if you're saying, we have this new treatment, well, you would be testing what that, if 17 or more got better. Not just exactly 17, right? It's always or more. Okay. So I probably beat that drum. All right. Is 6 a significantly high number of girls? Was it? What was the probability? So what was the probability for 6 or more?
0.1.
That's the chance of luck, remember? Is that chance of luck really, really believable? No, it's not low enough. It's supposed to be lower than 5%. Remember, the chance of luck is supposed to be lower than 5%. It's not. So we don't believe, that's not a significant, believable, important amount of girls. We think it was maybe just luck. So we say no, it's one of those no's. It's less than 0.05. No, because the probability is less than 0.05. Are we good on that? Is that making sense? significant results have probabilities with a lower than 5% chance of luck. All right. Let's move on. Number 9. So it's going to be the same exact thing. So 8 births, 8 set of parents. It's exactly the same. Yeah, so it's the exact same. And they're going to ask, find the probability getting exactly one girl. One girl would be 0.005. And then they say, what's probably getting one or fewer? One or fewer. That's going to be the significant one, right? Whenever they go to the end, 1 or fewer. Or 6 or more. Right? Whenever you go to the ends, that's how you test significance. So 1 or fewer, that would be, how would we figure out 1 or fewer? Add up both those, right? Because 1 or fewer means 1 or none, doesn't it? If you said we had 1 or fewer girls, we had 1 or none. So we would add those up. 0.008. So the chance of that is 008. Which one would help you determine it? It's going to be B again. So one of these that says B. Oh, is it answer C this time? Eddie, help me out here. Is that the answer they're given? Nerdy, is that the answer they're given? That's the right answer. I'm wondering if they got it together now. So it's not, 9 is not C. 9C is not C. Doing this, I'm starting to doubt myself.
Oh no.
Yes. Let's see. Since the probability, why is C not right? Since probably getting more than one girl is the complement of the result. Since getting 0 girls is an even lower number of girls than getting 1. Well, I don't like these questions. So D is right on that one. But this one, I still don't like D on this other one. Since the, what was it, C on this one? Since the appropriate is less than 0.05, or where was it? Oh, wait, no, this one. Yeah, since probably getting 7, since the probability of getting 7 or 8 girls includes getting 6 girls. Oh, they mean includes getting 6 or more. Okay, these are terrible questions. Sorry, I didn't realize how bad these were. They're not, okay.
So, that word is so wrong.
It is. Yeah, they mean to say includes getting 6 or more. That's what they mean to say there. Getting 7 or 8 girls includes getting 6 or more. That's true, right?
To do better is what they need to do.
Yeah, so on the test, I would phrase it, more correctly than that. Oh, you'll see when I make a practice exam. All right, let's move on. I'm getting tired of these questions. I'm sure you are too. All right, so we will go with their answers. So, yeah, we've done enough of these. Let's move on. Adults, blah, 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 same thing, same question. Number 11. All right, let's do this. Then we got to get on the next section. I want to do that. I want to try to do that coin flip for overtime football. All right, State's Pick 3 lottery. Here we go. Let's talk about playing the lottery. In the State's Pick 3 lottery game, you pay $1.13 to select a sequence of 3 digits. They're just making up some game. From 0 to 9. Such as 1, 2, 2. If you select the same sequence of 3 digits that are drawn, you win and collect $307.06. So they're just making up some kind of random game. Complete parts A through E. How many different selections are possible? So suppose they have this lottery game. See how this lottery game works? You pick a 3-digit number, like 723, or 565, or 829, or 014. You pick a 3-digit number. They have the random draw. If you got the 3-digit right on the money, you win $307. Otherwise, you lose your $1.13 you paid to buy the ticket. So, first question. How many different selections are possible?
1,000.
How many?
1,000.
Yeah, how do you know?
Because 000 also.
Good job.
All the way to 999.
10 to the 3rd.
Yeah, right. Either way, correct. So, yeah, because you could have from 000 to 999. That's 1,000 different numbers. Let me. If that seems confusing, let me help it this way. How about 1 to 999? How many from 1 to 999? 999, and then add in the 0, because 000 is one of the options, huh? Do you understand the logic he was using? That's right on the money. There's 1,000 different selections possible. Or what Brian was pointing out is he's using probability. He was saying 10 digits times 10 digits times 10 digits is 1,000. You're right, there's 10 digits in the first number, 10 different possibilities there. 10 possibilities for the second digit, 10 for the third. Either way you want to think about it, there's 1,000 different codes, 3-digit codes. There's 1,000 different ones because there's basically 1,000 different numbers. From 1 to 999 and 000 is your 1,000th. Okay, so what's the probability of winning then? What's the chance you're going to win? 1 in 1,000, huh? Because there's 1,000 different possible things that could be drawn, and you just have one ticket. So your chance that it's yours is 1 in 1,000. That's your chance of winning. Part C. If you win, what is your net profit? What are you going to get if you win? 307.06. Is that right, or do you?
You subtract.
Yeah. Do you have to? Do you not get? Yeah. I guess you have to subtract. Yeah. Do you see why? Because they're asking for net profit. They're asking for net profit. So when you win the $307.06, you still had to pay the $1.13 to buy the ticket. So the net profit to your bank account, what is it, 305 something? 93, I think. All right? So your net profit would be $305. And we have to be real exact with this. This is a science here. Be real exact. So you would profit $305.93 because you still had to pay for the ticket. D, find the expected value. In other words, is this worth it? What is the expected value? How do we calculate expected value? That's going to be the L1, L2. Expected value is the X bar. That's what that is. I don't know if you're used to recognizing that phrase yet. Expected value means average value. It means the average result. What do you expect on average to happen when you play this game? So you're going to do the L1, L2. What are we going to put in the L1, L2? What are the different... Think about when we're going to make... This is the first one where we've made our own probability distribution. So think with me on how to do it. What are the different things that can happen in this game? If you buy that ticket, there's two things that can happen. Win or lose, right? If you win, how much are you going to win?
307 or 305.93.
Yeah, 305.93. Let me move this over. Right? You with me? And what's the chance that you're going to win that? 1 in 1,000. If you lose, how much are you going to lose? So you got to make it negative because losing is negative to your bank account. And what's the chance you're going to lose?
999.
Yeah, 999 out of 1,000. There it is. Put those in your calculator. Does that make sense how we came up with that? Yeah. It's just amount of money times probability, amount of money times probability. And the losing is negative, because that's a negative effect. Here about the X bar. I got X bar is negative 0.82. How far do you want around? 100th, yeah, that's it. Negative 0.82. Did y'all get that? Negative 0.82? With the X bar, when you put the L1 and L2 and you hit the buttons on your calculator?
Yep.
So what does that number mean? What is that negative 0.82 in real life?
That's how much you're losing every time.
Yeah.
How much you're paying.
Yeah, on average, you're expecting to lose 82 cents. Even though you think, well, how do you lose 82 cents? You're either losing $1.13 or you're winning a bunch. True, but on average, it's like you're going to, if you played it thousands and thousands of times, it's like you'd lose 82 cents every time you play. That makes sense? That's really the value of the ticket, 82 cents. So if you bet $1.13, the expected value, yeah, there it is. So... And then they're asking some kind of question. What's their question? Which bet is better? A $1.13 bet in the pick 3 game or a $1.13 bet in the pick 4? Oh, so then there's a pick 4 game. If you bet Oh, those are the same. Yeah, so they're saying some other game has the same number. So neither is better because they're the same expected value. That's what they're looking for there. Does that make sense? They made up some other game, gave us the answer, gave us the expected value, and said, how does this compare to that? So that's how you compare games. Casino games, any kind of random luck games, that's how you compare it. Does that make sense? We good there? All right. Are we almost done with this section? Yeah. Last one. Oh yeah, this is good. This is the other legal gambling industry. What's the other legal gambling industry? Insurance. That's what insurance is. You ever thought about it that way? That's exactly what insurance is. They live and die by the expected value calculations as well. It's all a bet, isn't it? All insurance is a bet. My dad used to always say, life insurance, what's that? You're betting you're going to die. And that's exactly right. You are betting you're going to die. Of course, that can be wise because the people depend on your income. But anyway, all insurance is a bet. Fire insurance on your home, right? You just pay out unless there's a fire, and then they pay you, right? Yeah. So So you're betting. All insurance is a bet, isn't it? Insurance on your car, right? So loss unless you need it, right? So all insurance is a bet. That's how insurance companies calculate. It's all a legal bet, is what it is. So there is a 0.9987 probability that a randomly selected 31-year-old male lives through the year. A life insurance company charges $169 for insuring the male will live through the year. If the male does not survive, the policy pays out $120,000 as a death benefit. So let's figure it out. That's basically betting. It's exactly what it is. I believe in this betting. I have life insurance. But that's what it is. Let's be clear. That's exactly what it is. So the value corresponding to surviving the year is, so if the person survives the year, from the perspective of the 31-year-old male, if he survives the year, what did buying that life insurance policy do to his bank account? If he lives through the year, then he doesn't get any money. Right? So the effect to his bank account is minus $169. He just pays for the insurance, the $169 charge, right? And his bank account goes down $169, doesn't it? How we doing? You guys getting tired? Am I making any sense? Am I doing the wah-wah-wah voice at this point? Is that making sense? So if he lives through the year, he collects nothing, he just pays $169. What if he does not survive the year?
Gain.
Then his loved ones gain.
It'll be 120,000 minus.
Yeah, because he still had to pay the $169 policy, so they gain $120,000, but minus the $169. So they basically gained 119. My calculators tell me 831. That's the gain if he dies during the year to his loved ones, right? So he lost the 169, but they gained 120. Net effect, he gained a bunch of money. At least his loved ones did, right? That's all making sense? Does it feel funny to treat life insurance like a bet? That's exactly what it is, mathematically. All right? So let's go on with it down here. If the 31-year-old purchases the policy, what is his expected value? What's the worth? This is exactly what insurance companies calculate, the worth of the policy to them. How are we gonna do that? Well, this is L1, L2 again. Whenever they ask us expected value, that's X bar that comes out of an L1, L2 table. Okay? Let's make the L1, L2 table. Can we do it?
Yeah.
So what are the different, remember you think about, just like the last one, remember what we did in the last one, we said you can win or you can lose for the, whatever it was, the lottery thing. So what's going to happen with the life insurance deal? Live or die, right? If he lives, what L1 is the money, right? L1 is the money and L2 is the probability. Getting the hang of that? L1 is always the money. L2 is always the probability.
Would it be negative or?
Yeah, so you tell me if he lives,
Negative
That's the negative 169, huh? If he lives through the year, then he just lost $169 by paying for that account.
So would you like 1 in 365?
Yeah, what's the chance? What's the chance over here? What's the probability he's going to live through the year? They actually told us.
0.9987.
Right there. 0.9987. Do you know what those are called? The insurance people have a name for those. They have charts on you and I. They know the chance you're going to live through the year based on your age, your gender, your health. They can give you the number. Those are called mortality tables. It's also cold, isn't it? Is they put all the numbers up. But they're out. You can type them into Google. Mortality tables. Type in your age and whatever. You can find it. It's a science to the insurance companies. It's math. So the chance that the male will live through the year, 31-year-old male, is 9987. Okay, so and if he dies, what's the money for dying? That's the 119 number, right? So if he dies, his loved ones profit 119,831. And now what's the chance he's going to die?
0.0013.
Yeah, you go 1 minus, don't you? Right? If the chance he's going to live is 9987, then the chance he's going to die is 0013. And then just type them into your calculator. Hit the buttons, find the X bar. I'll do it too. Negative 13? Did you guys get that? X bar is negative 13? That's what I got for X bar on my calculator. Exactly, negative 13. So the chance... So that's the value of the... what does that mean? What does that negative 13 number mean? Anybody know? What does that mean in the real world, that negative 13 number?
He has a 0.13% chance of dying.
No, that's not a probability. That's money. See the dollar sign?
He's in debt.
Oh, he pays.
That's the value of the policy. In other words, on average, the insurance company looks this way, and they say, on average, he's going to lose $13 by buying that policy. Now you think, well, you can't lose $13. Right, but thousands of males, 31-year-old males, buy this policy. Most of them will live through the year, and they will pay their $169 to the insurance company. Maybe 1 or 2 will die during the year, and the insurance company will pay out to their loved ones. When it's all said and done in average, the insurance company will make about $13 per policy. That's what that number means. It's the average payout per policy. Or the expected value. So remember, expected value is an average. It's just like the gambling, right? Every time you play the roulette, on average you're going to lose whatever that was, 7 cents or 70 cents or whatever it was. Right? It's the average. So anytime you buy a life, so that's how the insurance company looks at it. They say we're making $13 per policy on average. Is that good? Is that making sense?
Yeah, probably the hard part is writing the table out, what to write.
Yeah, the table is the hard part, huh? The live and the die, the percentages.
Win or lose.
Yeah, the win and the lose. Yeah, practice those. Those will be on YouTube. You can watch them again. Can the insurance company expect to make a profit? Yes. They can expect to make a profit. The profit of $13 for every 31-year-old male who buys a policy for a year. That's their expectation. Is that good? Are we making sense out of all that? Questions I can answer? Let me finish this. I wanted to get to the football one, but we're running out of time. Let me ask you this. Let me see if this expected value thing is making sense. What if you have a friend, and your friend tells you the following game? Your friend says, hey, roll a die. Roll a single 6-sided die. If you get the numbers 1, well, how about this? If you get 1 through 4, you lose $2. If you get 5, you win $5. If you get 6, you win $6. Should you play that game or not? So if you're a friend, say you have a shady friend that says, hey, let's play this game. Roll a die. 1 through 4, you lose $2. 5, you win 5. 6, you win 6. Should you play that game? Or what if the casino offers this kind of game? Should you play that game?
It's like a half chance of winning or losing.
What's that?
Like a half chance of winning or losing.
That's more than half.
Be 2 out of 4.
Yeah, 2 out of 4, 2 out of 6 that you're going to win, right? 2 out of 6, 4 out of 6 that you're going to lose something.
2 out of 6.
But you win more if you win than you lose.
Chances of winning though. You can go keep going, keep losing.
So, what do you think? Should this be a game you'd play or not?
No. I would play a slot machine.
How do you decide the answer scientifically?
I don't know.
In our I don't know. I'm tired. Let's calculate it real quick in our last 3 minutes. All right. If you roll 1 through 4. If you roll 1, let's do the L1, L2 chart real quick. If you roll, here, I'll come over here. I'll do my L1 chart. Roll 1, 2, 3, 4, 5, or 6, right? If I roll a 1, what's going to be the effect on my bank account? -$2. -2, -2, -2, right? If I roll a 5, what's the effect on my bank account? +5 and +6, right? And L2, remember, L2 is the probabilities. I want to give you one more. The L1 is always the money. Get this. This is not part of it. L1 is always the money. L2 is always the probability. So what's L2? What's the chance for each of these things? What's the chance you're going to roll 1? 1 out of 6, right? Isn't the chance of rolling a 1 out of 6?
Are you doing decimal?
Yeah, your calculator will turn it in. Can you do that real quick? So put that into your calculator. Does that make sense how I'm getting the hang of these, laying these out? So L1 is always the money. L2 is always the probability. So put that in real quick. 4 plus -4 plus 11. The answer should be, X bar should be 0.5. I think. Unless I'm messing up. Yeah, I think that's it. You guys getting that? Am I going too quick? 0.5. Anybody get that? Tell me I'm right. I'm hoping I'm right. Tell me I'm right even if I'm wrong. I'm hoping that's right. You get that? Leonardo, you got that in the calculator? 0.5. Good. So what does that mean? Should you play that game or not play that game? So remember, X bar is not probabilities. I know you guys are seeing the decimal. You're thinking probabilities. Remember, that's money. Remember, the X bar is always money. It's not probability. Don't be fooled by the decimal.
You lose 50 cents a game.
What makes you say lose, Ken?
0.5 to negative.
It's negative?
To me. I don't know how to explain it, but to me it's you lose 50 cents a game.
Is it negative or positive?
Positive?
Yeah, notice that's a positive number. It's not negative. All the other ones we did were negative, weren't they?
Yeah.
In other words, if your friend offers you this game, play it. He's a fool. And the casino would never offer this game. You will win. This is positive. On average, you will win 50 cents each time. 50 cents each time, on average. Does that make sense on that? It's positive. So really, the casino is never going to offer this game because you would win on average with this game. It's positive. All the expected values are negative for the casino games. All right.